Hello friends, we are going to look at another medium level problem today. The problem number is 22. It's a medium level problem. It says generate parentheses. So we have a very simple description over here. Given n pair of parentheses, write a function to generate all combination of a well-formed parenthesis. So we are given with a number, say number 3, and we need to generate all the well-formed parentheses. So if I have a number like say 1, so only possible output could be this. We cannot do this. This is not well formed. So this is correct. So over here with the input like 3, what we can generate is we can generate multiple options, bracket open, bracket close 3 times. Then it could be something like this. It could be something like this. It could be something like, there could be so many combinations. Yeah. So we need to come up with all these parentheses. So we need to return a list that contains all these valid parentheses, well-formed parentheses, well-formed. So when we say well-formed, so well-formed means that it should have a proper opening and closing, as I've just mentioned. So we'll go to the whiteboard and see the solution for the same. So say we are given with the input, say 3. So what does this means that we can come up with all the combinations using 3 open brackets and 3 close brackets. So we need to generate all those combinations over here. So we'll look at the solution. Before we look at the solution, I would highly recommend that you give it a try yourself, and you can pause the video and think of a solution, and then you can resume and watch my video from here. So let's look at the solution. So let's say let's consider this input only. So let's say the input is 3. So 3 means we have opening count of 3 and we have a close count of 3. So opening count of 3 means we have 3 open bracket, and the closing count 3 means we have 3 uh, closing bracket. We'll see a recursive solution in this case. We'll use recursion to and come up with a recursive solution. So when I'm starting, I do not have anything at level at the root level. I do not have anything, and we have six inputs to choose from. So which one should I choose? I cannot choose this. It cannot start with a close bracket, right? It means that it is not well formed because this is going to be the first character of my output, right? So what we are going to do is we are going to write a function, and wherein at every stage we are going to check what we can uh, what is the best that we can do. So at the root level, say I have the opening count denoted by OP as 3 and close count denoted by CL, which is 3. So here the only one character, if I have to choose, I cannot choose from this group. I cannot choose from this group. I can choose from this group. So I can use one opening bracket. That's the best I can do using only one character. So when I do this, what happens is I go to the next level of the recursion. In the next level of recursion, what happens is I have already used. So what I have at this point is this, right? And I have a opening count of 2 because I have used 1 and a closing of 3. So I am in a state like this. Now from this state, what I can do is I can either open a bracket. So this will give me 2 paths, right? I can either open another bracket or close this bracket, right? So from this level, what all can happen is I can come to this, or I can come to this. So if I come to this state, what will I have? I'll have a opening count of 1 and a closing count of 3. And if I go to this state, what will I be left with? A opening count of 2 and a closing count of 2. So here you must see that there exists a condition that I can only use the closing bracket. I can only use this closing bracket when closing is greater than opening. When the closing count, so at this state, you can see I could branch into two sections because I have a more closing than opening. That means I have already opened one. So I could close one or I could open another one. So you can see the difference over here. So again, from this state, what could happen is I can come to a state like this. I can open three, or I could come to a state like I already have two open. I could have one close. These are my possibilities. But in this case, since I have a opening and closing, closing is not greater than the opening. So what does that means is we cannot close any further bracket. What we can do best at this stage is I can open another bracket. So I'll have a thing like this, wherein my OP count would be, so how many opening we have used so far? We have used two, so we are left with one. And how many closing we have in hand? We have two. So you can just see that one opening we have consumed over here, so the opening is decremented. Similarly for this also, my opening count becomes 0 and my closing count is 3 intact over here. And for this guy, we have the opening count of 1 and closing count of 2. So from this branch, so you can see that we are generally forming a recursion tree over here. So from this guy, what can happen is I do not have any more openings. So the only option am left with is closing a bracket. And we can only close when closing is greater than opening. So you can see here that closing is greater than opening indeed. So we can close one. And now at this state, what will happen is we have the opening count 0 and closing count of 2 because we have used one. We cannot have further branch from here because we cannot open. So there can be two possibilities, either open or close. So coming to this part, so here again we have one opening. So what what we can do from here is we have two closing and this one, right? So we can open one more. So in this case, what will happen is we are left with opening 0 and closing. We have used one, so we are left with two closing over here. Or what we can do from this state is, since closing is higher, greater than the opening, so we can, so this was my initial state, right? We can choose to close it as well. So in this case, what will happen is we'll have OP1 and CL1, right? You're getting it, right? So we are just going by one constraint that closing should be greater than opening if we have to use a closing, right? So from here, again, we do not have a choice anymore. The only choice left is to close because opening is already 0. So what can happen here is we can do this and we will have OP equals to 0 and CL equals to 1. It cannot have any further branches because we don't have any closing. Okay, so from here, what could happen is here also you can see that we do not have any further openings. So the only possibility for me at this stage is to close a bracket. So we already have this and we close this. So again here OP equals to OP still remains 0 and closing becomes 1, right? Um, and now we have used the closing, so no further branches is possible since OP is 0. And we have done for the closing part. So from each place, what we can do is we can create two branches, either to open or to close. And we are bound by the constraint that is mentioned over here, that whether we can use this closing or not. Okay, now coming down to, we will get to this branch soon. First, let us complete this part of the tree. So here we have one opening, one closing. So I can do one thing over here, that is we already have this, so we can open one more. So opening becomes 0 and closing becomes 1. Let me just rewrite this. It's very cluttered. Closing is 1. We cannot uh, create a branch to close because closing is not greater than opening, so we cannot create a branch over here. So now coming again to this part of the tree. So what we are left with is only one closing. So what happens is we already have this, we close this. So here you get OP0, CL0. So this becomes your base case. So this becomes your base case. And when you hit your base case, this result is added to the list that we'll be returning. So in the list, we get our first result as 3 opening, 3 closing. Okay, now coming to this part where we have one closing left. So we are bound to use that. We don't have any other choice. So here also it becomes OP0, CL0. So this becomes our second result, right? Similarly for this guy as well, we have one closing left and we are not left with anything. So here also OP becomes 0, CL becomes 0. And the result we get is this. So this is, again, you can see that these are all my base cases and I'll be adding it to the list. So you can see that we are generally started getting our results that we are looking for. Okay, so here also no other branching was possible. So coming to this part of the subtree, so where are we at in this part of the subtree? We are basically at, we have opened. So now we are left with two choices again from this branch. So let me, okay, I'll try to adjust it in this space. So we are using the opening of closing over here, so we can reach a state like this. So our opening is at 1 and closing is also at 1 because we have consumed it. Okay. Or what we could do over here is that we are at this state and we open one more, right? So in this case, what happens is our open count becomes 0 and close count become 2. Okay. So this condition here, it's ensuring that our braces are well formed. So this is ensured by this condition. This condition is enforcing that. Okay, so coming to this next part, now again I have one option over here. I cannot close from this state, right? Because closing is not greater than opening. The only thing that I could do is to open one more. And if I open one more, our OP becomes 0 and our closing becomes 1. Similarly, at this state, I am not left with any more closings, right? Any more openings. So only thing that I could do here is to close a brace. And this get me to a state opening 0 and closing 1. This tree will go on further towards the base case. So what will happen is, this is the only possibility wherein I will hit opening 0, closing 0. So once I reach the base case, I could add that to my result. So you can see it, that all of them are unique. Since we are going by the recursion, we are exhausting the space or exhausting the amount of inputs that we have, and we are slowly coming to the solution. Okay, you can see, right? Yeah. So from here again, we have one more possibility, that is to have something like this. So we are left with one closing, so we are closing it. So it becomes opening 0, closing 0. And we could add this result to our list. So we got 5 results. And so let's go back and see. So you can see that we have 5 results over here. And the way I showed you, this is how in a recursive way we can reach to the result. So we'll quickly look into the solution. So you got the problem, how we are exhausting things and getting our things done. So let's go back to the editor and try out the code. So what we are going to do is basically we need to return. First is that you need to notice that we need to return a list. So we need to have a list. So what I'll do is I'll create a list of string where I'll get the result and I'll call it as, and we are going to return this result. So before that, what we'll do is if n is passed, if n is, I'll say that less than or equal to 0, if n is passed with n. So in this case, what we are going to do is we are going to return collections dot empty. We are going to return an empty list in this case. That means we did not get a result. Now we talked about generating it using a recursive function, right? So we are going to have a function which will help us to generate. So let's call that function as generate. So what does that what will that function take? So before we go there, so let's come here and complete this function generate. So one is like open count. So I need to know my how many open is remaining. That is denoted by open count, and I'll have something called close count. So this is just to keep a track of how many open and close counts we have with us at this moment. So initially what will happen is it will be nothing but it will be n. So as you have seen already here that initially our state is 3 and 3 and our input was just 3. So if a 3 is given as an input, that means I have 3 openings and 3 closings. So that's what we are doing over here, nothing else. And at every step, you can see that we have calculated an intermediate result until we reached our final result. So as we pass on in the recursion, we need to have that string result stored somewhere. So I will have a string over here, which we'll call as result. So at every point, we will add to the result and send. So initially, I'll be sending an empty string because I don't need to send anything to this function. Let this function build upon it, upon the inputs that it is getting and get it done. And say I have a list of strings. So this list of string, we'll call it output, is nothing but this list where we'll be accumulating all our results. Okay, so this is the function all about. So what we are going to do in this function is so first let us put our base case over here. If open count is 0, if we have no more open count and our close count is also 0, so that means we have exhausted our option space. So all the options that we have has been exhausted and we are ready to add whatever we have got so far in the result. So what is the result? The result consists of nothing but these intermediate strings. So what we are going to do is in the output, uh, we have a list called output. We are going to add result to the output and we don't need any further processing. So what we are going to do is we are going to immediately return from this recursion. We are going to stop the recursion, not going any further. And also I have told you that the main condition is that is my close allowed or not. So when is my close allowed and when it is not? So it is nothing but this condition. Closing should be greater than opening. That is our condition if we are allowed to use a close at this point of recursion or not. So close count is greater than open count. So this will have a Boolean value whether I should be able to uh, close a bracket or not. So now what we are going to do is if there could be a case wherein I might have only close remaining. We do not have any open. So if open count less than or equal to 0, or rather say we'll say the reverse. If open count is greater than 0, then only we will go into the recursion. So we'll go and call the generate with open count -1. So we are supposed to reduce a open count, right? And when we are and close count, we are not going to do anything. Close count will remain as is. But we are at this if condition, we are going to use one of the open bracket. So that's why we are decrementing one of the open bracket count, and we are passing it to the next function. But when we are doing so, what we need to do, whatever result we have, we are going to add a open count to it. So initially it might be blank. So if I am using one of the open count, so initially your state might be blank, right? So at the next step, what I'll do is I will append this and send to the function. So this is your initially called. So if I'm using one of the open brackets, I'll pass like this. So the input to the next function would be nothing but your open bracket with the counter decremented, right? And we are not going to do anything to our output. The output remains as is. Now, the second part is we are going to see if close is close allowed. Then we are at this point we might have two branches. So at certain steps like this, you can see that we have both the option open, either to open or to close. Okay, so this close part is called only when your close is allowed. So we are going to check if close is allowed, then we are starting two branches from here. One is for open and the one is for close. So firstly we'll check is close allowed, and close count should be greater than 0. Only in that case I can go into this recursion. So generate will call again with open count, and we are going to reduce one from the close count. And what we are going to do is with the result, now we are going to append this closing bracket, and output remains as is. So yeah, we are done. So this is the entire function that's going to generate all your valid well from parentheses. Okay, I have a mistake over here. I did not pass the result. Some syntax error maybe. Is close allowed. Is close allowed. Sorry, this is close CNT, not count. So you can see that we were able to successfully generate for all. So if my input is 5, we will see that we have a lot more combinations of brackets that we can generate. So let's submit this code and see. So yeah, our code runs pretty well at 1 milliseconds, faster than 84% of the submission. The memory usage is also not that high. So yeah, this is my approach towards solving this problem. I hope you enjoyed the problem. It's a very nice and tricky problem. Hope you like the solution. Do like, share, and subscribe. It will encourage me to create more videos. And thank you once again for watching. See you soon. Bye bye.